So what they did is they came up with a method called root mean square. So what we do is if I've got a +1 and a -1, if I do it and I add them together to get an average, this is going to be 0, right? And then of course if I divide that by 2, I'm still going to get what? 0. If I was to come up and square both these numbers, what happens when you square a negative number? So I'm going to come up here and bring up my calculator. Where's my calculator? Oh, here it is. So this is the way I square a number right here. I'm going to say 1. I'm going to make it minus, and then I'm going to square it. What did it do? Turned it positive. Okay? That makes sense? So if I was to come up here and square the 1, it would come up to be 1. If I square the minus, it's going to turn it into a positive 1. I can add them together. Now if I divide it by 2, I come up and get an average. But it's not the true average, because the true average would be 0. Does that make sense? So if I was to come over, here on my alternation, and for all the positives, I square all the positives, and then I square all the negatives and add them together. Well, when I square the negatives, they would turn into positive, right? And I add them together. That means then I take what we call the mean of it. The mean is another word for the average. So I would square all the an infinite number of voltage measurements around the loop, or a very, very large number. And then I would take the average of it, and then I would take the square root. And this gives me what we refer to as the effective voltage. It's not the average voltage, it's the effective voltage. And this is what we call RMS, root mean square. So if they don't tell you, if they say 120 volts AC, that is RMS. And it's not peak. Peak would almost have to be 170 volts to get 120 volts worth of work. Peak to peak would be about 340 volts to get 120 volts worth of work. Right? You understand that? Because why? Why does it take so much voltage? Because it goes to 0. It's only at peak for a very, very small amount of time. So all our voltages are in RMS. Now, if it's a sine wave, it can always be so VRMS would always be equal to peak. We'd measure peak, and then we'll multiply it by 0.707. So let's take 170 and multiply it by 0.707. I think it's 170. Yeah, 120 volts. So it takes, if that peak is 170 volts, then we would get 120 volts worth of work out. Now, this is the difference between this meter . Oops. I'll look at this meter, and there's really nothing on it. I'll look at this meter, and I'm coming down at the bottom. Can y'all see what that says? It focuses in on it. 2 RMS. So what's the difference between this meter? This meter uses 0.707. So this guy here would only work with sine waves. If I put it into a non-sinusoidal waveform, this would give me the wrong measurement. This guy right here has a microprocessor in it, or a processor, and it calculates RMS. So this guy right here would give me the effective voltage of any AC waveform. This guy will not give me the true voltage of any AC waveform because all it uses is 0.707. Which one costs more? The true RMS cost. If I had a fluke, one of these is a fluke, and one of these is a fluke, this guy would cost more because this is true RMS. Who needs a true RMS meter? If you're dealing with sine waves, if you buy a true buy a true RMS meter and all you deal with the sine waves, you spend a lot of money for nothing. If you deal with variable frequency drives or switching power supplies or stuff like that, and you don't have a true RMS meter, then it's going to show you the wrong measurements. So if all you do is deal with sine waves, don't buy a true RMS meter. You're wasting money. That makes sense? It's like me going out and buying my wife an expensive laptop when all she does is get on Facebook and play games. All right, I go out and buy, a laptop that's got, 8 gigabytes worth of memory and all this speed, and she plays games on the thing. Chats every once in a while. But if you're in high level graphics and all that other kind of stuff, if you write video games and stuff like that, then you're going to need probably the best computer out there. So so you go out and buy the newest cell phone that's out there and you don't use none of the features that's available to them. All you do is get on Facebook or Snapchat or something like that. You could have got one of the cheapest phones they sell and it would have been just fine, right? And of course, you wouldn't have been able to brag about it. So people say, what phone you got? Which my granddaughters say all the time. When I go get a new cell phone, I always get one back. So I've got a 5. But it does everything I want. Need to do. Plus some stuff I don't ever use. I don't ever use, what's her name? Siri, yeah. I don't ever use her. Never. Okay, guys, I'll take a break. Never. Except asking her what's 0 divided by 0. You ever did that? With Siri. She'll put you down. So everybody basically know the difference between, so what's the average DC, what's the DC average of an AC cycle? 0. And that gets a lot of people hurt because they'll have their meter on DC, not think about it, put in there and they think there's no voltage there. And actually it's got 120, 240 volts there. So be real careful there. So make sure when you use a meter, verify the settings before you turn that power on, right? Or before you put a voltmeter on there, make sure you got it set up. If you got it on amps and you put it in the circuit wrong, you could create a short circuit. You could create a short and burn stuff up, or you could create a short circuit and really cause some problems, right? You understand that? Using meters are okay. It's just like before you back your car up. You just don't jump in some people do. You just don't jump in your car and back up. What do? You look, you check to make sure nothing's back there before you start pulling out. Of course, my wife's van's got a backup camera on it, which is really neat. She don't ever use it. She don't like using it. Ever since I had my wreck, I can't turn all the way around, so I really like it. Standard AC voltmeters measure RMF. These are going to be your cheaper meters, right? You understand that. And then you get these true RMS meters. Those are going to be a lot more expensive. But the average person does not need a true RMS meter. If you get into what we call variable speed drives for AC motors, anything that doesn't use a sine wave, then a standard meter would not measure those voltages. It would measure voltage, but it wouldn't be the correct voltage. And we just did this. Everybody okay on resistance? So wires has resistance. And this guy right here, the length of that one has about 0.5 ohms. Now you say 0.5 ohms is not much, right? You understand. But if I was trying to put 30 amps through that wire, then it would drop 15 volts. Y'all understand that? So wire has resistance. If I push current through resistance, I get a voltage drop. So I've got a piece of wire. Let's say the wire going to my battery and my starter. So here's my battery. Okay, and then it's a little different than that. And here's my starter. About how many amps would you think that starter takes to turn your engine up? Takes a lot. Small ones probably around 50, 60 amps. Big trucks, maybe 100 or so amps to start those. So let's say it wants 60 amps. And my cable, I've only got 12 volts to work with over here, and this cable only has 1 ohm of resistance. Well, V is equal to I times R. So if I come over here and I say, well, V would be equal to 60 times 1, that means that wire would try to drop 60 volts. Well, by George, I don't have 60 volts to give it. So my right, it wouldn't turn it over. So what happens is that, remember, power varies with the square of the voltage. So every conductor has an R. What determines how much R it has? No. Well, number one. Yeah, the material is made out of. Okay, and copper has the least. Aluminum has a lot more. Right? You understand that. What's the next thing that determines? The length. And 3, the size. Temperature is the last thing I'd put. I'd probably put size second. And then 4th would be the temperature of the conductor. So what do I need to do? So if I went out there and got a little old, 14 gauge wire that I run in my house, and I connected that from my battery to my starter, and I hit my starter switch, that 14 gauge wire would just probably disintegrate. It'd burn up. Because as soon as I try to pull all that current through that wire, then we're dealing with I square R. Power is equal to I square R. So that I square, it sees the current as squared, right? You'll understand that. And my wire is going to get extremely hot and it's going to melt. So what would I do? What do I have to do with that wire that runs from my battery down to my starter? Now, what do we need to do? If I'm using copper, well, I gotta use a strong enough what? Size for that length. Now, the battery cable is very small, right? You understand that? And this is why people, when they put big power amps back in their trunk, if you look at it with an oscilloscope, it actually the power going to your power amp actually pulses with the music, because the dang wires coming from your battery are dropping voltage. Now, you could use extremely big wire and have a hard problem running it, or you could put a battery or something in the back there. That's what people do. They'll put a big old capacitor back there to support it when it pulls a bunch of current. So what we're very concerned with, so what determines what wire I use? The requirements of the load, how many amps that load's going to need, right? You understand. And how far that wire's got to run. That's what determines the size of the wire we use. There's two things. It determines the size of the wire. What gauge wire you use is what type of load you're trying to, what the current demand of the wire is. Now, what the insulation of a wire determines is how much voltage it can keep in. So a 24 gauge wire would run fine on 1,000 volts. It's just that the insulation would have to be real big, right? You understand? The only thing, two things determines the gauge of a wire and that's not true. There's three things. The only three things that determines the gauge of the wire you choose is number one is how much current does the load need. Not how much voltage, how much current does the load need. Another thing is the length of the wire, right? You understand? The length of the wire. That's going to, and of course the temperature is going to run. So if we look at the current gauge, the current carrying capacity of in the NEC, National Electrical Code, it gives two ratings. It gives one for 70 degrees centigrade and it gives one for 90 degrees centigrade. And that's what insulation you would use and how much ampacity the wire would have at those different temperatures. If you run it outside those temperatures, then you're going to have to adjust for temperature. We do what we call a duration temperature. So this wire has an R. And where do we know the R at? Well, we can measure it or we can look it up on the American Wire Gauge. An American Wire Gauge gives us the resistance over 1,000 feet or over a kilometer. So I could, if I know the resistance over 1,000 feet, then I could calculate the resistance over 1 inch, right? To understand that, well, all we'd have to do is just reduce it down. But that is free air at 20 degrees centigrade. So if it goes above 20 degrees centigrade, what does that mean about the ampacity of the wire? Is it going to go down or go up? It's going to go down. If the temperature goes down, the ampacity goes up. But the problem is that what you do in the National Electrical Code, when it calculates wire gauges, it does it for the worst case scenario at those temperatures. It's called you get it in National Electrical Code, but it's real easy to find. It's NEC table 3. It's easy to find if you remember what the table is. NEC, I think it's 310.16. The new one is jumped to 15, by the way. So here's the ampacity chart. Put out by National Electrical Code. But that's not going to be big enough, is it? Sorry, guys. I should have it. I don't know where it's yeah, here's 316 right here. So this would be in the NEC, a National Electrical Code book. That's not it. So that was labeled wrong. This is not a good one. That's somebody that's came back. I was trying to, one of these is the actual chart that's in the code book. it's open somewhere. No, dang. Undoubtedly, I've overwritten it. Because I tried this one, right? I tried that one. We'll go back and just, this doesn't show up real good, but this is, that's the template. So what we have here across the top, and we'll look at that later on, is, so this is what it's rated at. It's rated at, this insulation is rated at 60 degrees. This is at 75 degrees centigrade, and this is at 90 degrees centigrade. And these are different insulation types. And here's the ampacity of a, and this is wrong. Originally what they did on a 14 gauge wire, they rated it at 20 amps. But when you ran 14 gauge wire in the house, you use 14 gauge wire for a 15 amp service. So on the new code, they've actually went back and rated it at 15 amps. If I was to look at the ampacity chart for the American wire gauge, it says the ampacity of a, let's see if this is it. It says the ampacity. So we use a term called ampacity. Y'all know what would y'all think that stands for? Right here it says ampacity. There it is right there. What does that mean? Yeah, that's the maximum amps a certain gauge conductor can handle. Y'all understand that? I'm going to start calling names here before long if y'all don't start answering my questions. And we'll see how smart y'all actually are. So y'all need to speak up and participate in the class. So a 14 gauge wire, it says it has a what? 32 amps. Okay. But it says it's in what? And what does that mean? What does free air mean? What would y'all think? So what would you think free air means? I mean, they don't charge for it? James, what would you think free air means? Sorta. Give me your name again. Anthony. What would you think it means, Anthony? Huh? No. What would you think, Albert? Huh? Free air means it's uninsulated. These are uninsulated wires. These are uninsulated wires. So they're out in free air. They're not insulated. As soon as I add an insulator to the wire, what would happen to the ampacity of the wire? Salih, would it go up or go down? So when you wear a jacket, you get colder. Okay. What's the four things that determines the ampacity of a conductor? One is the material. These are all copper wires. Okay. Number two is the size. Number three is the length. And number four is the temperature. When metals get hot, their resistance go up. So if I insulate this, I can't get 32 amps anymore. Y'all understand that? Can't get 32 amps anymore. Okay. And if I operate it above 20 degrees centigrade, I can't get 32 amps anymore. Y'all understand that? So what is 32 degrees centigrade? So what I would do is I would come up here and I would take 20 degrees centigrade, I'm sorry. And what's the conversion? So I'd take 20, I'd multiply it times 1.8, and then I would add 32 to it. So that means if I operated above 7 degrees centigrade, Fahrenheit, about 68 degrees, what's going to happen to the ampacity? Is it going to go down or go up? If the temperature goes up, what's going to happen to the ampacity of the wire? Is it going to go down or is it going to go up? It's going to go down. Y'all understand that? So this chart right here is nice. It just gives us a relative current over these different things. Alabama Power would use it because a lot of their wires are uninsulated. Why do they leave them uninsulated? Why don't they insulate those wires up on the power lines? Because if they insulated them, the temperature of the wire would go up, the heat that the wires generated would go up, and they couldn't carry as much current. That makes sense. Plus, it costs a lot more money. So they'd either have to go to a bigger gauge wire or just leave them uninsulated, right? You understand? So that makes sense. So when we look at the NEC cable, what it's got is it's got different types of insulators on there. And it gives the ampacity of the wire at different types of insulators. And that wasn't the right table. I have to find the new table. The new table is 315, by the way, 315 dot, what was it? 310.15 or something like that. So if you wanted to go look at the new cable. What was happening though is in the old code book, they said a 14 gauge wire had an ampacity of 20 amps at 70 degrees centigrade. Well, the problem is if you was an electrician, you never used, if you ran 20 amps, you used 12 gauge. And if your 20 amp service was 12 gauge and a 15 amp service was 15 gauge. So that got people so dang confused that in the new code, they rated at 15 amps. Now, why rated at 15 amps, even though it could carry, with that insulation at that temperature, it could handle 20 amps? Well, what you're trying to do is you're trying to choose a gauge that will work in anything that you can think about. So if I come up here and I use a 14 gauge wire on a 15 amp circuit, it would work up in Alaska, it would work in Alabama, it would work down in Hawaii, right? You understand that? So all these different temperature ranges, what they're doing is they're gauging that wire for the worst case scenario. So in the wintertime, the high might be 32, and then in the summertime here, the high, the temperature might be 100. Instead of me changing wires out just because my temperature is real high, what they do is they rate it for the maximum temperature that's been recorded in that area. So 14 gauge wire rated at 15 amps, it could handle 32 if we didn't insulate it. It could handle 32 if I didn't run it above 68 degrees centigrade. But as soon as I put insulation on it so I can put them together, right, you understand, and as soon as I raise those temperatures up in those walls, then we drop it down to 15 amps, and it works for just about every scenario that we could come up with. Unless I tried to run it more than 100 feet. If I try to run it more than 100 feet, then I'm going to have to do something about the length now, right? You understand? So as long as I keep it below 100 feet, then 15 amps will be great. As long as I don't operate it at 200 degrees, then 15 amps will be great. As long as I don't insulate it anymore than it's already insulated, then 15 amps would be great, right? You understand that? So that's what the code does. So these ampacity charts that they give us in the American wire gauge, remember, these are what? These are in what? Free air at what? 20 degrees centigrade, which about 70 is pretty standard for rating things. 70 is usually for ambient temperature. For rating solid state devices is at 70 degrees Fahrenheit, 25 degrees centigrade. Just about everything is right around that range because that's a pretty average temperature. Because American wire gauge has no idea exactly what temperature you're going to run it in, and American wire gauge has no idea what insulation you're going to put on there, right? You understand that? Now, NEC can do that because house wiring has standard insulations. So, and commercial wiring has standard insulations. So now they can rate it, okay, if you run this type of insulation on there, then at this temperature, then this is going to be the ampacity of the wire. Does that make sense? And NEC uses 3 temperatures. What were they? 60, 70, and 90 or something like that, where these wires are rated at. And that's very important in this class because that's what this is called. What? What's the name of the course? Yeah, so if you go in there and you install the wrong cable, what's going to happen? If you install the wrong wire gauge, number one, either you're going to spend more money than you need to spend, or you're going to have problems, either when you install it or when you don't install it. I mean, later on, right? And you'd hate to be responsible for burning somebody's house down just because you used the wrong gauge wire, or you did not terminate it correctly, or you did not insulate it correctly. Okay, so what's the things that determine the resistance of a conductor? That sounds like an excellent test question, right? In the order of importance. Yeah, number one would be the material. Number two, yeah, the size. Number three, and number four, and of course all this is determined by the load. What load are you going to connect to this, right? Y'all understand that? And not what the voltage requirement of the load is, or not even what the power requirements of the load is. It's the current requirements of the load. How much current does that load need? Are we okay? Any questions on that? That's an excellent question. Does the voltage have anything to do with wire size? Yes or no? Huh? Does the voltage have anything to do with the wire size? Yes or no? What do you think, Sully? What do you think, James? I didn't ask about amps. I says, does the voltage determine the gauge of the wire? Anthony? Ira? Has nothing to do with the gauge of the wire. What the volts determine is how much insulation you got to put on that wire. That wire looks at current. That's all it is. It's current. Right? You understand? It's just like pipe. What determines how much water gets through a pipe? It's the size of it. The size of the wall determines how much pressure you can put in there before that thing blows out the side. Right? You understand? And that's the thing true on the insulator. So what the insulator out here that we insulate this wire right here, this is by this. That sucker's set by volts. How much volts that wire's got to keep in. That voltage is trying to push current through everything, right? You understand that? And we've got to keep it in. It's just like when you get up in Alaska, you're getting rid of heat. So how do you keep heat in? Well, you keep what? You put on a jacket or put on a coat. And that's what we're doing here. We're trying to keep that difference of potential between me. We're trying to isolate my difference of potential between me and then that outside world there. So this guy right here, the insulation that I put that conductor in, that guy is what's rated in volts. Not the conductor. The conductor's not rated in volts. It's the insulation that's rated in volts. Y'all understand that? And plus the insulation is also rated in an environment. So like if you're going to run it in an oily environment, you need a certain type of insulation for a certain type of volts and that kind of stuff. So the insulation determines the amount of voltage it can keep in or keep from getting out, and it determines what environment we can run that in. And that same thing true with pipe. Sometimes they use plastic pipe, sometimes they use concrete pipe, right? So it depends on what environment you're going to put that pipe in. Sometimes we use metal pipe. Sometimes we use different types of metal. Sometimes we use PVC pipe, plastic pipe. And what determines that is what environment you're going to run that in. So we don't like to run metal pipe through concrete because metal pipe and concrete don't get along with each other. So most of the time when they run conduit through concrete, they run it through. You either have to have concrete rated metal pipe or you use PVC or use plastic. There's a lot of stuff to run in wire, ain't there? Like cable splicing, all I got to learn to do is hook up wires, but this is cable splicing and installation. So installation means we got to learn about the wires before we install them, right? And we'll learn how to pull them in the class. In fact, we'll do a lab over in the commercial wiring. I'll let y'all pull wires using fish tape and stuff like that if y'all hadn't had commercial wiring. Reactance and impedance. Unlike resistance, reactance varies with frequency. And devices called capacitors, as frequency goes up, capacitor reactance goes down. And devices called inductors, as frequency goes up, inductor reactance goes up. Now, if we get inductance and capacitance in the same circuit, we refer to that as impedance. And this is going to become important because when we get into communication cables, we're going to talk about the characteristic impedance of the cable. And so these are wires that are handling a frequency, right? Understand that. So the only way I can get impedance is if I have reactance. So everybody understand those terms? Yeah, so that's why, you know, if you took the cable coming into your house and you cut it open, you would see two conductors. You'd see one running in the middle, and then they would have an insulator around that, and then across the top they would have another conductor. That's metal. And so the metal runs out here. And of course those never touch because so we have a conductor, we have an insulator, and we have metal. This is called coax cable. There's two wires. How many wires is an extension cord in? Has it 2 wires? So why can't I just hook up an extension cord? If I break a cable, or if my cable's not long enough, why can't I just splice this and solder a piece of extension cord there, and solder an extension cord there, and run it into my next TV? There are 2 wires. It's 2 wires. Well, this wire, that coax cable, has what we call a characteristic impedance. The characteristic impedance of this is totally different between the characteristic impedance of that. And what would happen is that you wouldn't see a picture on your TV. We'll understand that later on when I show you. We have something we refer to as impedance matching. And this is a characteristic impedance of a cable. And if you screw up impedance matching, then you're going to have problems. So this network cable up there, that's a 100 ohm cable. And that's not a resistance, that's an impedance. So if you measured that with an ohm meter, you're going to measure almost 0 ohms. If you put 100 megahertz on that thing, it would represent 100 ohms worth of impedance. Not resistance, impedance. Right? So it's very, very important that we understand that when we get into communication, because most communication cables have a certain impedance. And that means you have to maintain that impedance or you decrease the integrity of the system. My father-in-law, his cable was running across his yard. He had a big old yard and lived way back off the road. So his cable ran a long way. He was pulling a big old truck in there one day and hit his cable dropping from his TV and broke that cable in two. Well, he got him a big old ladder and went out there and just twisted the wires together. And his TV picture was crummy. Because what he did when he twisted those wires together to splice them, he changed the characteristic impedance of the cable. So it's very important when we do things and we look at terminating the network cables. So we'll learn how to do that. We'll learn how to terminate network cables, how to splice them, and all that kind of stuff. And you just can't twist wires together. You got to maintain the impedance of the cable. If you screw up the impedance of the cable, then you're going to change the speed of the network. You don't want to do that, right? And you're not going to increase it. You're going to always do what? Decrease it. So even if you don't understand impedance at all, this is reactance. It varies with frequency. Every cable has a certain reactance, and that's what we have to maintain. We have to maintain that reactance. over length. It's really, really neat. So coax, we either have what they call 75 ohm cable or 50 ohm cable. That is not a resistance, that is an impedance. So if you measured the cable, it's going to measure like a wire. If you measure it with DC, because that's what your ohm meter does. Your ohm meter puts out DC. That's what it does. So you cannot measure impedance with an ohm meter. To measure the impedance, you would have to put an AC signal on the cable and then measure the current or whatever goes through it, or have an impedance meter. So what is impedance? It's a opposition that contains both reactive and resistive devices, and we'll look at some here in a second. What time does class get over? 12:45, right? I know these long classes are awful, and I'm sorry about that. You got to learn a lot. The first lab we'll do, and we might go ahead and do that just to break. Not today, but we'll do it on Monday. And we'll lecture a little bit. Is measure the wire gauge of wires. Now we're going to measure the diameter and use that to determine the gauge. And of course, we're not going to use that big old formula. Didn't I show you all the formula? This is the formula for calculating wire numbers right here. So how many people do you think use this formula? Let's see. Oh, it's not in this slide. Dang. This must not be the current slide. It's a long thing. I mean, it deals with powers and exponents and all kinds of things. So normally, when you determine the gauge of a wire over time, you can recognize them by just looking at them. If you don't know that, then you have to use either what we call American wire gauge, which we don't have anymore. Somebody took it, I guess. And the company that we ordered it from, I'd have to figure out where to get them from. We just can't order from anybody. They have to be on an approved list, and it takes a little while to get people on an approved list. Guys, where was that at? Oh, that's not in this. This is the only one we've gone over, though, right? Wasn't there a picture of American wire gauge in here? So there's the thing. Now this is the only PowerPoint that we looked at. Yeah, that's this one right here. Introduction. That's the first one we looked at. So this is. These are the actual charts. So you can always go in. This is an American wire gauge, right? And if you notice, it's got the little units right here. This is what you slide through right there. So what you do is set up for circular wires. And what you do is if it slides through that hole right there, once you get it slid in, you can pull it out. This would tell you what gauge it is. So it's kind of like a filler gauge if you ever put spark plugs in. You know, you can buy a filler gauge, but then you've got those wires that are set up for different gaps, 0.35 and that kind of stuff, that you just slide it in there till you can slide it in. If you can't go through there, you know you're set too close and you bend it out. If it moves in there real easy, it means your gap is too wide, right? And you tap it a little bit to do that. This works on exactly the same principle. This goes all the way up to single aught wire. And this goes down to 32. I'm sorry, it jumps into the center. So this goes all the way to 36 gauge wire. The American wire gauge, I think y'all goes all the way down to a 41 gauge wire. So these guys are neat, but what we're going to do is we're going to teach you how to use a measuring device that even though you don't use it often, some people use it often, especially if you're like a machinist, is we're going to let you use a micrometer to measure the wire gauge. It'll just give you a look at another piece of measuring equipment that you might run into, and you'll understand it. And what we're going to do is we're going to measure diameter, and then what we would do, then we'll look it up on the American wire gauge to see what number it would be. So these are the micrometers we're going to use. We'll show you how to use them. Oops. It's called an outside mic is what we're going to use. And we don't have the ones with the digital readout. They got some that's got digital readouts on it. They look at $147. Yeah. So you adjust it and it actually gives you that. We'll show you how to read it on an analog, and it's not going to bring up the pictures. Let's go here. Yeah, so this is it. So these are outside mics. We got enough, hopefully, for everybody in the class to get to use those. And what we'll do is basically what you do is you just put your wire in here, you adjust it until this thing clicks, and then you read the dial. And that'll give you the measurement. And then you can take that and look it up in a wire gauge to determine the number. And it'll just give you a look at using another piece of equipment. You probably need to understand this one before you go to that one. So this right here is a lot more expensive. So we'll look at that. So when we come in class Monday, even if we're not through with this lecture yet, we'll look at how to use a micrometer, and we'll do that lab. And that way it'll break up the monotony. I know these long classes are awful, and I hated when I went through them in college too. It's something we got to live with. Huh? So a capacitor is formed when we bring two conductors close to each other. So let's swing my camera around. So an oscilloscope measures exactly what's there. So this is an oscilloscope. And then this right here is my function generator. And I probably need to get some tape. Tell me that masking tape. So this is my oscilloscope that's measuring the voltage. This is my function generator that's generating AC. And normally what we would do, of course, is we would come up here and we would put them together like that. So you can actually see this conductor is connected to this conductor. What I'm going to do is I'm going to come up here and I'm going to take my function generator and I'm going to tape it so it won't move. And then I'm going to take my oscilloscope and tape it up here. And I want y'all to see that they're not, in fact, I guess it would be easier to do it up here, right? So let's put it right here. And we'll put it right here. Now those two guys are not even touching each other. You see that? So these guys are not even touching each other. See that? Yet I'm sending a signal between those two conductors. How's that happen? Well, this is what we call, what I just did was created something called a capacitor. So all we need to have a capacitor is to bring two conductors close together. And thank God, if we didn't have this capacitive effect, there would be no such thing as cell phone. Where's the signals coming from my cell phone? Is my cell phone connected to wires? So what happened is that we got this big old antenna, which is one conductor out there somewhere. My phone's got an antenna in it. We call them antennas, but they're nothing but wires. And I'm sending those signals electrostatically through the air. So what we have here is we have a capacitor. This is not a capacitor. This is one side of the capacitor. We call them plates. We call this crosstalk. If you've ever been on something and hear people's voices that's not on your channel, we used to have a big problem when we used to mechanically switch. Instead, we electronically switch the phone system now. We used to mechanically switch it. And sometimes those wires wouldn't be real close together, and you would hear people talking strictly by a crosstalk. Now, what determines this? This is not done on purpose. Can you look at that? So what I'm doing, of course, is I'm changing what we call the capacitance. But what determines this capacitor right here is how much wire we have overlapping each other, the spacing between the wires. So if I was to get the wires closer together, you'd see that voltage go up. If I get them further apart, then it would go down. And then what I put as an insulating material. So as soon as I put my finger in there, you notice the coupling actually changes. So all I'm doing is changing the insulating material, what I put between the two conductors. Now, sometimes we get capacitors that we don't want, right? A lot of people call it stray capacitance. But we also have capacitors that we deliberately set the size of the plates, we deliberately set the spacing between the plates, and we deliberately set the insulating material. And these are capacitors. And they come in all sizes, all shapes. I'd have to get some. So this is a constant. Anybody know what pi is? Yeah, what's the number we use? Yeah, 3.1. Anybody know what pi is? Here we use 6.28. And then F is what? The frequency, and this is the size of the capacitor. So you can see if frequency goes up, what happens to opposition? It goes down. So the higher the frequency we have, the military, its radio frequencies are way up in the ultra high frequency band. And once you get into those extremely high frequencies, you have capacitors all over the place, and they're really, really hard to deal with. So that means it makes the communication very secure, because you'd have to have really, really, really sophisticated equipment designed almost perfectly to pick up those RF waves that they transmit between those signals on extremely high frequencies. Cell phones usually operate, I think it's around 2.4 gigahertz. So that's extremely high frequencies too. So that means these guys right here have to be extremely well designed. So that means they don't give these things away. Used to, they'd give you one pretty cheap with a 2-year agreement, but most cell phone companies have done away with that. And so now you have to buy your phone. So they give you a real good deal, and then you pay so much a month on these things, right? Every one of them I know of is going to do that. But what's nice is you can change your phone anytime. Originally, you could only change your phone every 2 years. You had to keep the same phone 2 years, because it took that long for you to pay the phone off. But now what can you do? You can go in and trade it in and start paying on that one too. So I usually change out when they stop working. Or I go swimming. I had an iPhone 3 that I went swimming with. I had it in the pocket of my swimsuit. Well, now you can say Rich did that too. So anytime I have two conductors that are running side by side, and I put an insulator right there, what did I make? I made a capacitor. And that's when this right here comes into play. So I get up in those communication channels like 10 megahertz on coax cable, 100 megahertz on that cable right there. Then I'm going to start thinking about capacitance, right? You understand that? So every cable has capacitance. Or when a conductor comes close to another conductor, we have capacitance. That's why when you're running power cables and you're running communication cables, if they cross, you always cross them perpendicular. You don't let them run side by side. You'll understand why now, right? So here, this is my capacitor right there. If I let a communication cable run next to a power cable, then I got a capacitor. So if you ever wonder why people say, well, you're supposed to cross them at 90 degrees. So if a signal cable ever needs to go across you need to do what? You need to keep it far away from it. And if they do have to cross, you need to do it at what? 90 degrees. Because now your capacitor is very, very small. Now, if you're in any type of communication system. And so cables, we do two things with cables. What are the two things we're going to send on cables? Either we're going to send power or we're going to send signals. You understand the difference, yes or no? So do you power your TV off your cable coming in from your house into your TV? No. What's coming through that thing? That is not power, that's signals. Right? You understand? Do you power your radio up off your antenna? So what's coming off that cable that runs from your antenna down to your radio? It's signals, right? Y'all understand that? So conductors are either going to carry what? They're going to carry what? Power, or they're going to carry signals, or they can carry both. Alabama Power tried to play around with sending cable TV over their power lines. They would get along perfect. But they had a big problem with those big old transformers out there. Those transformers impeded the signal so much that you couldn't get it through it. So they could jump around it, but that's where they had problems. And that would have made Alabama Power millions of dollars, you know, because now their power cables are only sending one. They're sending both power and signals. So never got it to work out. We used to do it all the time, you know, where we sent. You used to go buy a thing from Radio Shack where you could plug a unit into a wall, and you could plug your other unit into another a little unit, and you could turn lights off and on from anywhere in your house. So they were sending signals over the power, but it couldn't go outside your house because it couldn't get through the transformer, which was pretty neat. Of course, Radio Shack is probably any Radio Shacks around here. Last time I looked, they still said they had one over on Green Springs. Radio Shack used to be real neat because it was true electronic. Then they started going to TVs and cell phones and all that kind of stuff, and their electronic stuff actually started dropping down. Inductors. An inductor is an electrical conductor that has been looped into a coil. In a DC circuit, so in a DC circuit, a capacitor acts like an open. A capacitor will not go through, DC will not go through a capacitor. An inductor is nothing but wire. So this right here would be an inductor. Now, this is not a real good inductor. This is an inductor. I need to put this on video. And I'll show y'all this. This is really, really neat. And this will probably be the last thing to do. So all we need to do to get an inductor is just to have coils of wire. And the wires have to be pretty close to each other. In a DC circuit, an inductor stores the charge magnetically. Inductors make great electromagnets. We got an electromagnet around here somewhere. So this is an inductor. And what I'm fixing to do is I'm fixing to charge it up. So I'm going to come over and get my DC power supply. I don't know if this is going to work on this power supply. I don't know if it puts out enough current or not. Let's see. Okay. So I found a piece of metal. Okay. This has got some heat in it. I'm going to pick that up. I used to have a piece of metal up here. This will work for me. Okay, so it did what? And that's a magnet. So it's doing basically the same thing as this. So this is a magnet. I could pick it up with this guy right here too. So what's the difference? Yeah, I can come over here and I can turn this off. And I can turn it on. Or I can literally control the string. So I can turn it down so it won't hardly pick this thing up. So what we can do with this, we call these electromagnets. So if you ever seen movies or something where you got these big old round things that's coming over here picking up big chunks of scrap metal and moving them over, that's nothing but a electromagnet. They can turn off and on. But this is DC. So when I put DC on this, and I've got to use a lot of turns of wire because the only thing that's limiting the current in this conductor is its length and its material, right? You understand that? So this is very small gauge wire. We call this magnetic wire, by the way, because the insulation, how much magnetic field you get is determined how close you can get the conductors together, not the insulator, the actual wires. So magnetic wire has extremely thin insulation on it. So it gets warm. So the only thing that's, you can see it got up against the plastic because it's pretty high voltage. I'm sorry, so that's if I put DC on an inductor. But you got to understand, if I put DC on an inductor, it's like wire. So what determines the resistance of a wire? The material, the size, the length, and the temperature. So that's a lot of turns of very fine gauge wire. Because the only thing DC sees that is wire, right? But that's an electromagnet. As soon as I put AC on that thing, then it would be a true inductor. And if you take AC, they'll get you into a little more on how it actually works. Oh, so this is a transformer. This is one that got burned up in the somebody not hooking up an oscilloscope, right? So these are transformers. This is a multi-winding transformer, and I'll pass this around. If you look, all you see is turns of wire. So what we do on a transformer is we use the magnetic field being generated by one inductor, and we induce a voltage into another conductor through what we call mutual induction. We don't get into that, but that's the way it transfers. So all a transformer is two inductors. That's all it is. Now, what prevents this thing from burning up? If I put this on DC, it would burn it up or burn my power supply up. If I put it on the AC, then we have inductance. We have what we call inductance reactance, and that's what's limiting the current that's keeping this thing from burning up. So this is the transformer. It's bad. This came out of our training. This is done by somebody who's been up the stove for long. That I thought knew how to do it. So just hooking up test equipment wrong, if you don't understand how to hook up test equipment, especially these guys right here, then you can cause major problems. Wasn't too bad. I think it cost us $20 to replace it. When we first got the bid, it was like $99. And I was like, oh God, but then I realized that we had quoted $5. So that was a little. And when they send the quote, they didn't send it per unit. They sent it for the whole thing. So. Of course, that's part of learning, right? So we call it X of L. This is called inductive reactance is equal to pi FL. Now notice on the capacitor, it was 1 over. So the capacitor X of C was equal to 1 over 2 pi FC. Here though, so here if F goes up, it's on the top, that's frequency, then X of L goes up. So X of L, the opposition moves in the same direction as frequency. Frequency goes up, X of L goes up, even though inductors are manufactured deliberately, any turn or twist in a conductor, we call that stray conductance. I mean call it stray inductance is what we call it. But if I'm running 60 cycle, even though I have a wire twisted, it's not going to affect it because the frequency is so low. When those frequencies start getting up real high, that's when we got to worry about inductance, right? I've got to worry about putting loops in a network cable. How we call it a radius. How far do those loops need to get apart? So just running loops in a network cable can cause you problems. It could set up inductance. If I get the inductance too high, then I'm going to lose the speed of my network, right? You understand? So there's a lot more to understand in pulling wires, especially communication cables. We don't have a lot of problems with Alabama Power because the frequency is so low, only 60 cycles. We get into some of these communication channels, 2.4 gigahertz, 100 megahertz, 10 megahertz, then, we're talking millions, right? 10 million hertz per second. Then we're going to have to start worrying about what? We're going to have to start worrying about capacitance, and we're going to start having to worry about inductance. Because I can definitely screw things up by just by taking a network cable and looping it around my hand and putting a piece of wire wrap on it and not making that loop big enough. And we do inductors on purpose. They have a function in life. They do a lot of things. Normally we use, since they're in capacitors, since they're responsive to frequency, we use these guys a lot in what we call filters. Now what does a filter do? Well, that's what you want to go through and prevents what you don't. And if you understood this, if I put capacitors and I put a capacitor and an inductor in series, one after the other, them suckers try to cancel each other out. One of them varies in the same direction as frequency, the other one varies in the opposite direction. So we could set up what we call tuned circuits. That was the old days. That's the way radio tuners and everything worked. They worked off inductors and capacitors. And what we would do is we would make one of them variable. In fact, this is a variable capacitor right out of a tune. When we used to teach RF communication. So now we do it electronically, but it's still basically the same. But if you ever tear into an old radio, you're going to see something like this. So when you go out there and you change your station, what you're doing is you're changing. These are plates right here. So this is one capacitor. This is another capacitor. And when you adjust it, what you're doing is you're changing the overlap. So what determines the size is how far they overlap. So that's why when I run communications, I do this way so I decrease the overlap, right? So what I'm doing is I'm taking one side and I'm doing this. My capacitor is actually formed right here. So that's what we're doing right here. So this is one capacitor. This is the plates on one capacitor. They're hook them in parallel to make them bigger. This is the other set of plates right here. And all I'm doing is changing the overlap. And what are they using as an insulator? Starts with A. Iron. This required two capacitors, so here's our two tuning capacitors. This was used in a type of receiver called a Hartley receiver, which we're not going to get into. And it required two capacitors to tune in a channel, tune in a station. So what they did is they'd have a fixed inductor, and then what you would do to change your channels, and then they would have a cable that came down here, and it would move your tuning dial back and forth. I can show you one of these. We have one of our instructors that's got a really, really, really old radio that we're trying to restore, and it's got the tuning capacitor in it. So this is actually a variable capacitor. This is the way we used to tune radio. Look at some of the old movies when they're trying to dial in the channel, moving those dials. All they're really doing is changing the wall, changing the capacitor to come up to tune the circuit. So a capacitor and an inductor is going to tune at a certain frequency. They'll cancel each other out, which is pretty neat. We call it the resonant frequency, which is going to come into play with something we call impedance matching, which is pretty neat. So these are what capacitors look like. That's a tunable capacitor. We call it a variable capacitor. These things come in what we call electrolytic capacitors. These are deliberately created capacitors. So we deliberately create capacitors. We have what we call stray capacitance, and these are capacitors that we don't want, right? You understand? And how do I make a capacitor? All I got to do is bring two conductors close together and put AC on. How do I make an inductor? All I've got to do is have loops of wire. Right, understand. This is an inductor. That's all it is. This one I deliberately, I'm trying to show you. We'll show y'all that. I don't know if we'll get to it today, but I'll show y'all that what happens when I put AC on it, and I'm going to stretch it out. It's going to act like a conductor, and then when I start rolling it up, you'll actually see it start acting like an inductor, which is pretty neat. Have y'all seen that before? Pretty neat. Another thing that we get from capacitors and inductors is we get what we call phase shifts. And this is the last thing we'll look at. Let me do that with this inductor. So what I'm going to do is they'll come up here. I'll keep recording. We'll put this on video. What we're going to do is we're going to come up here and we've got this conductor that we're going to turn into an inductor. Bring it back around. what we got a little resistor. So voltage drop across the resistor starts going down. That means voltage drop across the resistor goes up, right? According to Kirchhoff's law, total voltage in the circuit has to drop. So voltage drop across this is going down. That means voltage drop across the wire. What we're going to do is we're going to come up here and we'll probably have to have a pretty high frequency. It should be okay. So what I'm going to do is I'm going to hook up my ground right here. And what is this? This is my function generator. So this is my common. And of course here's my common, and then on this side, we hook up the wire. So right now all we have is just the regular circuit, right? The only voltage drop we get would be what's required. This is a yellow violet black, so it's 47 ohm resistor. And then what we're going to do is we're going to look at one of our scope probes, and we're going to look at the applied voltage. See what's going on at the applied voltage. So that's what we're putting across there. And then we're going to take our other scope probe. I think it's hooked up to a real probe. And I'm going to look across the resistor. This is what we call a dual channel scope. What it lets us do is it lets us look at two signals at the same time. So we must have some clues somewhere. Because we got a phase shift already. Go down here and try to get those twists. Yeah, just close through the hand. They're slightly out of phase. And the difference here would be, of course, the voltage drop of the wire. So normally what would happen is this right here would almost mirror that. And what we're going to do, so the blue one is what's being transmitted. The yellow is coming across the resistor. And what we're going to do is we're going to start winding this up. Now I'm not changing the resistance of the wire, right? But what determines the resistance of the wire? Okay, so I'm not changing the R of the wire. I'm not changing the length of the wire. I'm not changing the gauge of the wire. All I'm doing is what? Yeah, all I'm doing is rolling it up. Now hopefully you can see what's starting to happen with the blue, what's happening with the blue. It should be starting down. And then we can see that the thing is out of phase. And you'll see what we mean by out of phase. If they were in phase, these would be on top of each other, but the blue is starting to shift to the left. And the more I wind it, the further the blue goes down. I'm not changing the R. If I was changing the R, I would have to be changing the length or changing the material. But the voltage drop across the resistor is going to that. So the voltage drop across the resistor is going down, so the voltage drop across the wire must be going up. What's causing it to happen? I'm not changing the resistance of the wire. It's this thing we call an inductor. X of L is equal to pi FL. I'm not changing the frequency, so what I'm doing is changing the L. So if L goes up, voltage drop goes up, which means there's less voltage drop. And notice the phase shift is getting worse and worse and worse the more I wind this up. I'm not changing the R, I'm changing the L. And I've got frequency on this thing. If I put DC on this thing, nothing would happen. It would act like a piece of wire that's this long right here. If I unwind it, it would come back out. So just those curls in that wire created an inductor with what I wanted to see. See, ain't that something? So this is an inductor. So all an inductor is just nothing but what? That holds water. That's all it is. So this right here, I could use this as an inductor. Or I could use an inductor that's set for a predefined size. So this guy here has a certain amount of turns of wire. It uses a certain gauge wire. So the inductor here would be fixed, right? You understand? Or if I have a turn in a loop of wire, then I'm going to set up an inductor. But if I was to come down here and change this frequency, well, let's lower the frequency. So let's get down. I'm sorry. Okay, so now they're right on top of each other. So we don't see a phase shift because the frequency is now down to 165 hertz, right? You understand that? X of L is equal to 2 pi FL. So I didn't change the L. I didn't change the L because I didn't add more turns, but I changed the L. So this is why we don't worry about turns of wire down at Alabama Power 60 cycle. We don't see a phase shift and we don't see a voltage drop. They're right on top of each other. But all I'm going to do now is start changing the frequency. Now, as soon as I start changing the frequency, we start seeing a phase shift. And notice the blue is going down. Now you can see a what? See a shift in phase. And so the higher the frequency, the worse the phase shift, and my inductor is dropping more voltage. The lower the frequency, but I'm not changing L now. So before I was leaving the frequency alone and I was changing L, right? You understand? Now I'm leaving L alone and I'm changing L. So when we start getting into these real high frequency signals that we see in communication, then it's very important that you understand when you start pulling those wires why things have to be done the way they're done. Why do we have to use coax? And we'll talk about that later on. Why, if I use straight wire on a communication system, why don't it work? And why do I have to use coax? Why do I have to use 50 ohm cable or 75 ohm cable or 100 ohm cable? We're not talking about a resistance. We're talking about a reactance or an impedance. You can't measure impedance with a voltmeter or an ohm meter. Everybody understand that? Here we could calculate it, but by how much voltage drop we have. This is a capacitor. I mean, this is an inductor. We would see a phase shift with a capacitor would be on the other side. So inductors cause what we call lags. Capacitors lead, so that would be on this side. And that's why they cancel each other out. But if we didn't have these phase shifts, there would be no such thing as a single phase motor. Why? Because if I put a single phase, I have no rotation. So to make a motor rotate, then the field on the outside, the electromagnet on the outside has to rotate. So three phase, we don't have any problem because when the first phase is going down, the second phase is up. But if I don't have a phase shift in a single phase motor will just hum at you. If we go over to the commercial wiring lab, y'all remind me of that, and I'll show y'all how a single phase motor reacts without that phase shift. So what we do, we have what we call capacitive motor, capacitive start motor. And what they do is they use a capacitor to create a phase shift. So the single phase motor will do what? It'll turn. A split phase motor uses inductors. So if you hear a split phase motor, like you'll find in a washing machine or something like a fan, most fans use split phase motor. And then, or you'll see a capacitor. So if you work on an air conditioning system, you'll see two brown wires coming out. You follow that over, it goes to a capacitor. You take the capacitor out and turn it on, the motor's going to burn up because it don't ever shift, it don't ever start. So we use these guys for several things. We use them to deliberately create what? Phase shifts, and we use them to respond to frequency. But we also have what we call stray capacitance, and we have what we call stray conductance. These are capacitors that you put in there by not running your cables correctly, right? These are inductors that you put in there by putting too many loops of wire in there or something like that. And then, of course, on low frequencies, it's no big deal, right? You get up into AM, you wouldn't have any problem. You get up into FM, and you don't run stuff right, you're going to have problems picking up your stations. Are we okay? All right, guys. So have a good weekend. So Monday, what we'll do is try to hold off here. This is about the end of the lecture anyway. And we'll look at how to use a micrometer, and we'll try to do some lab. So what do y'all need to bring? Safety glasses. Make sure you bring safety glasses.